circuit. So let's look at the example. In the circuit, as we can see here, we given you the circuit. We have given you the circuit and we are asking you to solve for the nodal voltages V1 and V2 using nodal analysis technique. So the first thing you want to look into the circuit is to recognize the nodes, as we said earlier. So this is the reference node or the ground, which is the node at the bottom here. Usually if you have the symbol connected to a node, that is your reference node, which basically means that this is going to read 0 volts in reference to any nodal voltage. Then we need to recognize the nodes in the circuit. So this is a node that exists in the circuit, and this particular node has a power supply, a voltage power supply connected to it. So this voltage power supply states that the voltage from this node to ground gonna equal to 20 volts. So the voltage of this node is known. Then we have those two nodes over here, node 1 and node 2, that are indicated in the problem. So clearly that V1 and V2 are not known because we don't have any voltage source connected from V1, for example, to ground and from V2 to ground. Then we are going to have this node, and this node also has a voltage source connected to it from this node to ground. That means that the voltage at this node is the same as the 10 volts. Now keep in mind that you need to check the polarities for those two voltage sources. Basically, we have two unknown voltage sources in the circuit. Once you have determined all the nodes in the circuit and the unknown nodes in the circuit, the next thing you need to recognize is that there is a dependent source connected in the circuit. Now this is a current source. This is a current source because it has an arrow. Basically, the value of this current source, the value of this current or this current source depends on Vx. Basically, this current will equal to 0.1 times Vx. So you need to look at Vx in the circuit, and then Vx is defined to be the voltage across the 20 ohm resistor or R2, where the plus polarity of Vx is on this side and the negative polarity is on the other side, as shown in the circuit here. Now when you do nodal analysis and you know that this current source here depends on Vx, then you need to define Vx in terms of the nodal voltages. That's extremely important. Why is that? And the answer is simple, because we know that the objective of the nodal analysis is to solve for V1 and V2, which are the unknown nodal voltages. Then you need to define this parameter Vx in terms of the unknown nodal voltages. So let's state that clearly, that we need to define the dependent parameter, which is Vx in this case, in terms of the nodal voltages. So that is extremely important. Then you can see that Vx is basically defined as the voltage from V1 to V2, which means that the voltage at V1 going to be higher than the voltage at V2 in terms of Vx. So you need to be consistent with the polarities here when you define Vx. Then we can state that Vx is basically V1 minus V2. The voltage across the 20 ohm resistor as defined in terms of Vx is going to be the voltage at this node minus the voltage at that node. And this basically is by KVL, right? So if you're going to say that minus V1 plus Vx minus V2, right? Solve for Vx, you get that. So we can define the voltage across this resistor in terms of the nodal voltages. Now it doesn't have to be voltage, it can be a current, for example. So let's say that if you have another circuit where we said that this parameter going to be Ix, where Ix going to be the current going through this resistor as example, right? Then you still can define Vx in terms of the nodal voltages. Basically the current going this way going to be this voltage minus that voltage over that resistor. So in any case, you always need to define the parameter in terms of the nodal voltages. So here we have Vx, which is V1 minus V2. Then you going to come to nodal 1 at V1 And at V1, where we have this node, you're gonna sum all the currents leaving the node. So I'm gonna start with the current on this branch. So the current in this branch, which is the 10 ohm resistor, going to be V1 minus the voltage here, which is the 20 volts over this resistor. So we're gonna state that the current going to be V1 minus 20 over 10. V1 minus 20 over 10. And then we are going to add the current going through this branch, and the current going through this branch going to be V1 minus V2 over 20 ohms. So basically it's going to be V1 minus V2 over 20 ohms. Finally, we're going to add the current going in this branch, and the current leaving this branch is minus the current going in, and the current going in going to be 0.1 times Vx. So we're going to say minus 0.1 times Vx. Those are all the branches connected at V1, so this is going to equal to 0. Now what we're going to do is we're going to substitute for the value of Vx, this value of Vx, we're going to substitute it by this value, which is V1 minus V2. So we're going to substitute Vx to be V1 minus V2. Then we're going to say that V1 minus 20 over 10 plus V1 minus V2 over 20, those are the same from the previous equation. Now we're going to substitute for the value of Vx. So we're going to say minus 0.1 times V1 minus V2. Right? That's basically Vx will equal 0. So all what we did here, we substituted for Vx to be V1 minus V2. Now we're going to group the terms together. So we're going to group the V1 terms together. So the V1 term is going to be 1 over 10 plus 1 over 20 minus 0.1. So those are the V1 terms. Then we're going to group the V2 terms. So we're going to say plus V2. So V2 going to have minus 1 over 20. And then here minus the minus going to be plus 0.1 times V2. And finally, the only term left is this term, which is the negative 20 over 10. If you take it to the other side, going to be plus 20 over 10. Now we are going to basically evaluate the equation and make it look nice. So once you evaluate the terms of V1 here, it's going to be 0.05 V1. Once we evaluate the terms for V2, it's going to be plus 0.05 times V2. And the 20 over 10 going to be 2. I don't like to use common denominators, even though it looked tempting in this problem. But I like to use basically the algebraic sums as I'm showing you here. If you feel you want to use common denominators, you can, and it works. So this is going to be the first equation that we have that describes the sum of the currents leaving node V1. Now we're going to use KCL at node V2. So we're going to come to node V2 and we're going to sum the currents. So I'm going to start with the current leaving the R4 here, which is the 10 ohm resistor. This current basically going to be this voltage, which is V2, minus that voltage, which is the 10 volts, over the 10 ohm resistor. So we're going to have V2 minus 10 over 10. And then I'm going to add the current leaving this resistor, which is the 20 ohm resistor, or R2. So I'm going to write it as V2 minus V1 over 20. So it becomes V2 minus V1 over 20 here. Finally, I'm going to add the current leaving R3, which is basically V2 minus 0 over R3. Or basically, you can say that V2 over R3. So we're going to say plus V2 over 20. And the sum going to equal to 0. So this equation, basically, we summed KCL at this node. All the currents are leaving equals 0. And now we're going to basically group the terms. So I only have one term for V1, which is negative 1 over 20. And then I'm going to add the V2 terms. So the V2 terms, I have 1 over 10, which is this term, plus 1 over 20, which is this term, plus 1 over 20, which is this term. And I'm going to take the negative 10 over 10 to the other side. So it will equal to 10 over 10. Now we're going to make the equation look simpler and nicer, or cleaner. So when I evaluate the negative 1 over 20, I will have negative 0.05 V1. And here for the V2, I will have plus 0.2 V2. and the 10 over 10 equal 1. This is the second equation that we have, which describes the sum of the currents at node V2. Now we're going to express those two equations that we have, equation 1 and equation 2, in the matrix form. So we enter it into the matrix form. We enter the coefficients of V1 and V2 in the first equation as a matrix form like that. And then the coefficient for V1 and V2 for the second equation in the matrix form. So that's what we have here. We multiply that by the vector which contains the unknown variables that are V1 and V2. And then that will equal to the other side of the equation, which we have 2 in the first equation, and we have the value of 1 in the second equation. Now, this equation is classical. We can solve it using any technique we want, such as back substitution. But I like to use the inverse of the matrix method, so I can solve for V1 and V2 basically by taking the inverse of this matrix, multiplying it by the vector with the values of 2 and 1. So then you get the answer, and that is the answer. V1 going to be 28 volts and V2 going to be 12 volts. So what's so special about this example is that we have a dependent source here, and when you have a dependent source, you need to define that dependent parameter. In this case was Vx in terms of the nodal voltages V1 and V2. So you do nodal analysis, you have a dependent source, look at the dependent parameter, define it in terms of the nodal voltages. And